Hello, welcome back. So today is the last week for this course and we are starting with lecture 58 today. We will have a few lectures this week and what we are going to talk about this week are about on-wafer measurement and de-embedding. Okay, that is a very important concept in microwave devices, and we will talk very briefly about the classes of operation in for power amplifier. Okay. So today's lecture will start on de-embedding and on-wafer measurement, and this will require a knowledge of the two-port network theory, that we talked about, the S parameters and the Y parameters, ABCD parameters if you recall. Those are the matrices with which you try to quantify the input and the output, and you try to study the device mathematically. We will need those, but we will try to also understand in what physical context do you need to invoke them. When we say de-embedding, what does it mean? Okay. So to the whiteboard here you will see that the topic that we are going to cover are fairly simple, at least in principle. We are going to talk about on-wafer measurement, de-embedding, what it means. First we have to understand what that thing actually means. So you make devices on a semiconductor wafer, right? You have maybe a gallium arsenide wafer, maybe gallium nitride, maybe even silicon LDMOS. When you have different devices on a wafer and each block represents devices, there could be source drain and then gate and stuff like that. So when you measure it on the wafer, it is called on-wafer measurement. Now this is not the only way to measure, there are many other ways to measure, and in real world actually you will need different approaches to measure, because in a on-wafer measurement what you have is that if you have an active device like that, you have like a CPW pad, which is a coplanar waveguide pad to measure the on-wafer devices, and you have seen this picture many times in the course, ground, signal, ground, so you have source on both sides and then in between maybe you have the gate, right? The gate is the signal. So these kind of structures are there to enable on-wafer measurement of say S parameters or power, things like that. However, in real world devices you do not need these giant pads, because those are adding to extra capacitances and parasitics, right? You do not need those giant pads. What you do is that you do not have those CPW, you just have the active devices with some pads for bonding, okay, and then you dice the wafer, okay. Now when you dice the wafer, there are automatic and manual dicing machines, of course they can dice it, and then what you do is that you take one die. So this die, for instance, this is your die. This die may contain a discrete device, okay. For instance, it might contain a multi-finger high power discrete device for power amplifier application, okay. It might contain a discrete device like that with source, drain and gate pads, right. Now this discrete device may or may not be internally matched, which means you give the device to a vendor just like this is. It is up to the vendor to design the matching network. There has to be a matching network in order to use it as a power amplifier. This is just a discrete device, correct. This is just a discrete device which is not matched, which means looking the output and the input, you are not going to see 50 ohm, you will see some complex impedance. So the vendor has to, or the designer has to design a matching network to make it look like 50 ohm, and then you have a board around that with all this matching network, biasing network, etc. And maybe then you say this is that board using the discrete die for which I am making either a power amplifier, or I am just making I am not making a power amplifier, I am just making an internally matched inside this board or maybe a package. I am just matching the device to 50 ohm termination, and now I am going to give this to a designer who does not have to take any headache or pain about designing the matching network. The people know that it is 50 ohm terminated, so they can just use this entire board probably to design a power amplifier or something like that, okay. This is not an MMIC. MMIC is a monolithic, so everything has to be fabricated on the die in the clean room, everything has to be fabricated, okay. So this is not an MMIC, this could be a hybrid MIC, a microwave integrated circuit, okay. But this die, discrete die, this die was just a discrete device in this case, okay. That is one possibility, it is just a discrete device. In some cases this die may also be internally matched on the die, which means while fabricating this transistor in the clean room or in the fabrication facility, you have already designed the matching network and you have implemented the matching network, which is also fabricated in the clean room using all kinds of lithography, metal deposition tool, etching, etc., such that when you take the die out, this die that you have diced out from the wafer, it has the discrete device, it also has a matching network. So then I will call it internally matched transistor, FET, internally matched. So then it is terminated at 50 ohm, it saves the vendor headache of designing an extra matching network, okay. There is also possibility that this discrete die can be just an IC. It could be an RF IC, maybe it has a switch, an LNA, a power amplifier or whatnot. It could be an IC, it could be an MMIC also, by the way, and then in that case the entire process is an MMIC process. So each die could be say an MMIC low noise amplifier or maybe an MMIC mixer. Okay, there will be many components, many passive components, like directional couplers will be there, splitters and whatnot, Wilkinson power divider. These are different microwave components to add the power, to combine the power, to split the power, and so on and so forth. So you can have all those components integrated, and there are designers that will design it, and so each die could be an MMIC, for instance. What I am just saying is that on the wafer, when you fabricate, you can have, when you dice them, okay, then you may have a discrete device, you may have a discrete device which is internally matched. You can have an IC, a generic IC, you can have an MMIC, it can be anything, okay, that discrete, the die that I am dicing out, okay. But once I have diced out that die, okay, I can sell, there are many commercial entities that will sell either a discrete device or maybe even a internally matched device or some kind of IC, MMIC, etc. Now in that case, measurement using on-wafer techniques are not suitable, because this is not an on-wafer now, it is a die level, it's a die level device or or an IC or whatever. So when you are talking about die level, then the measurements will be different, because you do not have these giant CPW pads here to enable a GSG probes to probe them, okay. What you instead have is that you need to bring in microstrip lines, and then there will be SMA connectors. You will see the images, I will show you. These are SMA connectors, for instance, or some kind of coax cables, because these cables are the ones that will connect to the tool, the VNA, the vector network analyzer. I will show you. The vector network analyzer measures the S parameters of the device, for instance. So to the vector network analyzer, I will have this coaxial or SMA connectors cables, which has to connect or hook to this semiconductor substrate using microstrip line. So the microstrip line will basically convert this propagating electromagnetic wave in the RF signal, essentially the RF signal in the SMA, to a planar form, which is a microstrip. It's a planar form, and then it will propagate in the semiconductor substrate. It will go through the device, mixer, whatever, amplifier, etc., etc. So then the measurement is different. You are not talking about an on-wafer measurement. Okay, you are not talking about on-wafer measurement, because it's a diced die. Okay, it's a die, and in many cases the die will be packaged. You need a package, of course, for so many reasons. Sometimes it may be packaged, and the entire package may be available for purchase. Okay, so company might sell a discrete die, a board, a internally matched device, a packaged device, a packaged MMIC. It can sell anything. A company can sell anything depending on the customer needs. Okay, so then you can have a package, just a package, which is sealed and encapsulated. It's a package, and there can be many different types of package. You can have a single lead on both sides, you can have leadless packages. Okay, so there are many kinds of packages, and these packages, when you purchase them, you cannot characterize or measure these packaged devices using the on-wafer measurement techniques. Okay, you need to hook up the cable connector, and you do what is called connectorized measurement. Okay, connectorized measurement, and of course in a discrete die also you might have to do a connectorized measurement. In a packaged device you have to do connectorized measurement. When you say connectorized measurement, you are bringing the coax cables or the SMA connectors from the instrument and you are feeding them into the package. Okay, so then you have to do a connectorized measurement. Sometimes the package device might be placed inside a larger circuit board. You might have a larger circuit board of maybe a front end module or maybe even a power amplifier, and then you are going to put the discrete the package device in the board. We have seen some of these images in one of our previous lectures, if you recall. I believe it was during lecture of gallium nitride. I had shown you some images. If you can go back and see, you might want to put the package device on a board, and then that board, or maybe it's a front end or maybe it's a subsystem, that board will have the SMA connectors that will be connected to the VNA. So those are not on-wafer measurement. What we need on-wafer measurement is before dicing the devices. Okay, when the devices are there on the wafer, that is on-wafer measurement. Why do you need them? Oh, on-wafer measurements are extremely important, because they are very accurate, and the probe tips, probes, etc. are very widely available. They are very popular, and you can develop device models. You always need to develop device models when you characterization modeling, they generally go hand in hand, especially for things like MMIC. You need to do passive characterization modeling, active device characterization, small signal modeling, large signal, nonlinear modeling. So all these things will go hand in hand, and to develop model it is very important to do on-wafer measurement. You thoroughly characterize the device, you build a model. Once you have the model, once you validate the model, once you verify the model against measured data on the wafer, then what you can do is that you can get rid of the CPW pads. You can just have a discrete device which you are going to dice, maybe package, maybe match in unmatch. You can predict the performance of the device based on the models that you have developed by on-wafer measurement. Okay, the models will help you now predict or interpolate or extrapolate the performance of the device over a certain bias range, over a certain frequency range, over a certain range of device dimension. Okay, it will help you predict, for instance, how many turns of spirals are there in inductor, how many gate fingers, what is the gate width, W for instance. All these things you can predict. That's why on-wafer measurements are very important. In most academic labs you will start with on-wafer measurement only, and academic labs mostly do not go into, and at the device labs I am talking about, they dicing, packaging, etc. Then they move into the domain of the RF design. Even in academia there will be the RF design, RF IC group. At the device level, and because this course is not about RF IC or MMIC design, this course is not about microwave engineering, this course is about microwave and RF devices. So if you are looking yourself as a device person, then it's important to understand these concepts, but you have to understand that on-wafer measurements are very critical. Okay, they are very widely used, very popular, very widely available, these probe tips, these probe stations. Okay, and you can be very accurate, and you can de-embed the parasitics. I'll talk about that very well. You can develop and build models, verify, validate them, and once you do that, it's easy now for you to actually get rid of these pads, CPW pads. You can actually make devices that are for real world application. You can dice them, package them, match or unmatch. You can build models and you can predict their behavior. So that's very important. On-wafer and not on-wafer. Okay, when I say not on-wafer, I mean connectorized measurement. Connectorized measurement and on-wafer measurements, they have their own uses and their benefits. So we need to be aware of both of them. Now what is de-embedding? The concept of de-embedding, before I go to all of this, is that when you talk about on-wafer measurements only, okay, and even for package and die level measurements you will have de-embedding. I'll come to that later, but for an on-wafer measurement I told you, you will have source, drain, stuff like that, and then you have a pad, correct? This is the source pad, and that enables you, it's a and then this could be gate, for instance, this could be drain. So this is your source and which is your ground, and this is your source which is your ground, and this is your gate which is your signal, and this is your drain which is your signal. So of course your probe tips will come here, 3 probe tips. I'll show you images of that. Okay, 3 probe tips will come here. This is like a coplanar waveguide, and this is very common, very popular. It's very easy to use, especially for compound semiconductor based devices. This is very widely used, and when you have this kind of a arrangement to measure the S parameters, for instance, you can do pulsed IV, things like there are pulsed IV measurements. I'll come to that. Then there is load pull to measure large signal behavior of the device. Okay, when I say large signal, I'm talking about nonlinear. It's power. You're going to get it's important for power amplifier, for instance. You are going to get output power. That's a very nonlinear thing that we are talking about. Okay, so this is your active device. Maybe I can change the color. This is your active device, and everything else is actually just to enable a measurement. Okay, now of course you can have that. Why don't I just measure the active device? I just don't have the CPW pads. The problem is it's not a DC measurement, it's an RF measurement, so you cannot use the conventional needle probe. If you go to a DC probe station, you have this needle probe tips and you have a single probe. You don't have this 3 kind of configuration. You just have single probe tip, a single probe tip, and that cannot be used at RF frequencies. It will lead to a lot of errors. Actually, it will have noises, it will have losses. Okay, and it is not a waveguide per se. You need a waveguide to measure RF devices. So either you can use a microstrip or a strip line. Those are more complicated to implement in this kind of a transistor geometry, especially for on-wafer measurement. CPW, this kind of a coplanar waveguide, or a GSG is more convenient to implement. But however, strip line and microstrips are very widely used in MMIC design, not for enabling on-wafer measurement, but for actually implementing certain functionalities in the circuit. They are very much useful. You need to have this waveguide. So that's the reason you have this CPW, and you do that. Now the problem is these giant pads, they introduce a lot of series inductance, and then they will be in they will, because there is a ground plane, they will couple in parallel in shunt capacitively to the ground also. Okay. So this introduces parasitics, a significant amount of parasitics. This become worse with higher frequency, of course. So this, because of this parasitics, the measurement that you do will include the effect of the device, but also include the effect of this pad parasitics. You need to subtract out the effect of this pad parasitics. So that is called de-embedding. Okay. Because the device is embedded in a network of these pads, you want to de-embed those, you want to subtract the effect of the parasitic components introduced by these pads, so that you only get the behavior of the active device. Okay. So when you have an active device like that, okay, and then you have this giant pads, for instance. Okay. And so what happens is that there is something called a reference plane. Okay. A reference plane is very important. There is something called reference plane. Essentially reference plane tells you till what level, physical spacing or physical level, till what physical point are you going to subtract out the effects of these extra parasitics. Where is your plane? So for instance, if my plane is here, that means I am going to subtract out everything till this point, correct. My plane is here, so my plane is here and here, so I am going to subtract out everything there. Sometimes the plane may be here, which means this transmission line is not de-embedded. I am just giving an example. So the reference plane tells you physically where is that plane, till that point you are going to subtract the effect of the parasitics. That is called de-embedding. Okay. So that de-embedding is very important for this on-wafer measurement, because it will give you the true active device S parameters when you measure, because when you measure you are getting the S parameter of everything, but then when you de-embed you will get it exactly for that active device only, because you will subtract out the effect of the pad parasitics. Okay. Now S parameter is what you are going to measure, but then many of these operations will not be very convenient in S parameter, the mathematical operation, because the pad capacitances will be in parallel, the inductances will be in series. So you have to convert from S parameter to things like Y parameter, Z parameter, back to Y parameter and back to S parameter and so on. Okay. And then that is how you get the actual values of the S parameter. And if you want to plot gain, for instance, people plot H to 1, which is a hybrid parameter, so you have to convert to H parameter. So things like that. Okay. Now with this background we can actually go and look at de-embedding, but before that we need to again recap slightly about the small signal model, about the fact that the device is nonlinear. Okay. Device is nonlinear. And before I leave the initial discussion on the concept of de-embedding, I have to tell you it is not only the device on wafer for which you need to do de-embedding. Oftentimes you have to do de-embedding even for packages, even for die level discrete components. And there are things like fixtures, we will talk about that. Fixtures are basically arrangements, or you can say they are the, not package per se, they are the assemblies, the mechanical assemblies that will help you both mechanically as well as electrically establish the contact between the external coaxial cables coming from the instrument, for instance, and the active device which is planar. So you have this microstrip line and you have this assembly, a specific assembly that will enable you that measurement. Once you see the images it will become clear. So those are called fixtures. You basically, it is an interface between the measurement tool and the discrete maybe packaged or unpackaged die. Okay. You need the fixture to enable that measurement, because both may not be in the same configuration. So that fixture will enable that interface. So oftentimes you have to also use de-embedding for these discrete dies, or for fixtures, for packages. Also you might need to do de-embedding. You want to find out the parasitics that are introduced by the package leads, the package itself. You might want to find out the parasitics that are introduced by things like bond wires. You are going to wire bond the device to a board. The wires will also introduce parasitics. You want to find out what those parasitics are. You have to de-embed them. Okay, the package, the bond wires, the board, etc. So de-embedding is a universal concept. Okay, and here we will only discuss de-embedding in the context of a device, more specifically in the context of device, but the basic underlying principle stays the same when you talk about even fixture or package de-embedding. Okay, just have to understand the basic concept here. So now what we will do is that we will have to start from a recap of a simple small signal model of the device. Essentially we will try to see how the small signal device, a model of a device is generated or it's built conceptually, okay, from the fact that it's a nonlinear device. A transistor is a nonlinear, even a diode is a nonlinear thing. So from there we linearize. Matlab it means we are talking about small signal, where when the magnitude of the signal is small enough, you can linearize it around certain point. You can treat that the variations are linear around that small delta variation. So we are not talking about large signal. Large signal is the domain of load pull, where you are going to talk about large power output, a significant non-idealities like harmonics will come. You have to develop a non-linear large signal model for that. It is not within the scope of this course, but we will talk about a small signal model in the context of de-embedding. First, what will happen is that if I say that there is a device, and it could be a diode for instance, and it is a non-linear diode, and it is a non-linear diode, it is for instance a 2-terminal diode. Okay. And what I am going to do is that I am going to suppose I am talking about a voltage that I am applying V, okay, and then there is a current that is flowing I for instance. If I change the voltage by delta V, I am going to change the current by delta I. Okay, the small I and small v means that there is a small perturbation that I am giving. I can say that the voltage is a function of I, or converse also, and so any change in small voltage gives you, is a function of I plus delta I. Okay. Now how am I going to do that? If you recall a Taylor series expansion from your 10 plus 2 or maybe even undergrad, Taylor series tells you that if you have a function f of x plus delta x, then you can do is that you can do it f of x plus what? You can do the first derivative of f of x into delta x, remember, then you can do the second derivative of f of x into delta x square by factorial 2, then you can do the third derivative of x into delta x of cube by 3 factorial, if you remember this, and plus so on higher order terms. So what we are going to do is that we are going to say that, maybe I can change the color here, we are going to say that this part is error. Okay, those are the errors, the higher order terms, those are the higher order terms that I am going to ignore, the error I am going to ignore, and this is the part that I am going to take. Okay, this is the part I am going to take, this I am going to take as the approximation of the function. Okay, this I am going to take as the approximation of the function. So you can see this is a linear part, delta x f dash of x. So I am linearizing it, I am talking about this, and for this approximation to hold true, the error that I am talking about, the error should be much smaller than the approximation. Typically it should be like 0.01 times the approximation. Okay, whatever approximation you have, it should be 100 times lower than that, then that error should be lower than that. So then you can say that is okay. So now what I can do is that this delta V I can then express from this, I take inspiration from this Taylor series, and what I say is that I can say it is f dash of I into delta I, right. So the voltage perturbation is related to the current perturbation with this f dash of I, right. So now if I look at a 2-port network then, and this was a 2-terminal, but I am now looking at a 2-port network, it is a 3-terminal device. So this is a 2-port network, so I have a signal and a ground here, and say I am applying a voltage V1 between both of this terminal, so between the ground and the signal. On the output side I have say voltage V2 between the ground and the the signal here. The current that I am feeding in here is I1, and the current that is coming from here is I2. Okay. So now for any change in delta V1 here, I am going to get delta I1 here, correct, or maybe I can write a small I here, and for any delta V2 here I am going to get a delta I2 here, right. So now actually this current that is flowing I1 for instance, it's a 3-terminal like a transistor, it's a 2-port network, it's a transistor. So the current I1 will actually depend on both V1 and V2. Now I cannot say that it just depends on V1 because it's connected. Okay, it depends on both sides actually. In a transistor, if you look at for instance the gate current depends on gate voltage, but also depends on the drain voltage because that will set up the field. Similarly the drain current depends on the gate voltage very much, but it also depends on the drain voltage because there will be short channel effects, there will be output conductance and so on and so forth. So the current I1 and I2 will depend on both V1 and V2. So I have two different function f and g, and I am looking at the and they are depending on both V1 and V2 essentially. Okay. Now what I do is that I can just say that the current I1 and I2, the perturbation in I1 and I2 that is happening. Okay. This perturbation in I1 and I2 that is happening, I can write in a matrix form as a function of the perturbation that I am giving V1 and V2. You can think of this as actually like equivalent to the gate voltage and this is like the drain voltage, the output voltage, and that is the input voltage. This is like the gate current I1 and I2 is like the drain current. You can think of that qualitatively like that. Okay. So then I am going to express this perturbation in the current as a function of the perturbation of the voltage. Okay. I am looking at the small signal model development. I am looking at the linearization of the I have used the linearization of the Taylor series expansion here. Okay. Now essentially what is happening here is that if I have current here and if I have voltage here, then this matrix is what is has to be multiplied with voltage that you get current. You have to multiply admittance, right. Admittance is 1 by you can say impedance or resistance. So this is admittance, and admittance means it's Y. So I am looking at a Y matrix here. Okay. I am looking at a Y matrix here, and this Y matrix, essentially this Y matrix that I am looking at here, which is essentially Y11, Y12, Y21 and Y22. This is the Y matrix, but in reality Y1 and all these things are essentially what? They are basically, if you recall in the previous slide I told you I1 is a function of V1 and V2. So that is the Y11 actually is the that function V1 V2, okay, with respect to V1, that is Y11. Y12 is basically the function V1 V2 with respect to V2. So how is it perturbing with respect to V2? That is pretty much what is happening, and similarly Y21 and Y22 will be G V1 and this will be G V2. Those are the things that are representing. Okay. So I am representing the function with respect the partial differentiation because it depends on both V1 and V2. So I am looking at the partial differentiation and I am trying to this is the input voltage, this is like the gate voltage, and this is the output voltage, this is like the drain voltage. Just remember that. Okay. So this is the Y matrix is relating to the current perturbation with the voltage perturbation. This is all fantastic, but I have to build a physical model of this. I have to build a physical understanding of how this is going to help me build a transistor small signal model. Now if you look at this carefully, so what is happening is that I can write this matrix as, maybe I can change the color so that the contrast is better. So what I am going to do is that I can expand the matrix and say that I1, instead of delta I will just write I1 is equal to Y11 into V1 plus Y12 into V2, right. I can write that like that, and I2 will be equal to Y21 V1 plus Y22 into V2. Okay. So now what is happening is that let's build a model. Maybe I can go to the next slide. So what I am going to say is that I had a 2-port network. Remember I had a 2-port network. So I am going to use the same 2-port network. So this is V1 for instance, and then I have V2, okay, V2, and I have already written down the equation of I1 and I2, which is I1 equal to Y11 V1 plus Y12 V2. Okay. So what is going to happen? This is V1, so I have to multiply this V1 with Y11, and that is a admittance. So it is in parallel, it multiplies. So if I have a Y11 like that, it could be anything, a Y11, then this Y11 is multiplying by the V1, and so this basically gives you I1. So essentially your I1, okay, I1 is this, but I1 also has a component this, and what I am going to do is that I am going to just model it as a current source. So I1 has this first component and the second component. So I1 has this component and this component. This component is Y12 into V2, depends on V2 here. Okay. Now similarly I have I2, which is this is Y21 into V1 plus Y22 into V2. So I am going to have one Y22 here because this which multiplied by this gives you this component. So that is component here, and then there is another component here which is basically Y21 into V1. Okay, that is a component here. So this is your I can say you are building a small signal model based on this Y matrix that we discussed, right. You can quickly see that this point, this actually is your drain current, okay, and this drain current is basically a representative of your GM. So Y21 is actually GM, the transconductance is basically how much gain you are getting. It's from the input side to the output side, what is the gain, into V1 is nothing but VGS. V1 I told you it's basically your input voltage VG, correct. So this is actually the current and the source and drain, and this is the source, of course this is the drain, this is the gate, that is how I am building it, this is the source, right. And this Y22 actually is your R0, which is the output resistance. you want the output resistance to be infinity so that this you don't have this term, but this is the slope of the IDVD. If you are plotting ID versus VD, then you have a certain slope like that. That slope is your essentially output resistance, output conductance you can say. So this is R naught, and that can include other factors also, but this is largely the R naught here. Okay. Now this, maybe I can use a different color again just to make the contrast better. This component is basically ignored. Why do you know? Because this component is basically telling you that there is this is the drain. So there is a signal applied at the drain. Okay, there is a signal applied at the drain which is getting kind of amplified at the gate. That does not physically happen. Think about it carefully. A signal applied at the drain is getting amplified at the gate and coming out of the gate. That does not happen because you are putting the gate current is very low, and the signal at the drain is not getting amplified and coming out of the gate. Okay. So this component actually is meaningless. So this component does not exist in reality. We are trying to build a model here. So then this is the small signal model. This is fantastic, this is the small signal model, but in a real small signal model there are like 15 to 20 different components, but here we have only 3 components. We have component 1, component 2, component 3. Okay. Component 2 is basically your GM-VGS current source, component 3 is your output resistance R naught, and what is component 1 here? Component 1 actually is your CGS, although it looks like I have given a symbol like a resistor, it is basically your input capacitance, the capacitance between the gate and the source. Okay. So that input capacitance CGS is what is going to be multiplied by the gate current IG in order to get the gate voltage. Of course you have to look at the proper impedance here to get the gate voltage. Okay. You have to take omega C and stuff like that. So these are only 3 components, but in reality you have like I don't know 15 to 20 components. Where are those components coming from? In a real small signal model you have so many components. Where are those components coming from, and how will you add them to this network? Okay. This is the genesis of the small signal model, and this is for a field effect transistor, but it is very similar to build up for even a bipolar device. Instead of CGS you probably will have CB, the base emitter capacitance. Instead of the output, this output resistance will still be output resistance, and this probably will not be GM-VGS, this will be essentially GM into VBE. Okay. So things like that, but the basic premise is similar, although we are talking about a field effect transistor. So the question now is then, how do we build a small signal model for a realistic device starting from this base? And although we have talked about small signal model a lot in our gallium nitride discussion, in our gallium arsenide discussion, in our bipolar device discussion, in LDMOS etc., this is truly the fundamental way in which the small signal model is being built. Okay. But what I will do is that I will end the lecture here now, because we have introduced sufficient concepts in this lecture, and we are going to transition to the next lecture where we are going to talk about a real small signal model. How do you transition from this base to a real small signal model vis-a-vis or with respect to a real transistor. Okay. A real transistor, when I say real transistor I am talking about a small transistor on wafer, I am not talking about a package for now, but even then there are so many components there. So we are going to see where those components come from, and then only we will go and talk about the de-embedding. Okay. That is the main goal here. So thank you for your time. I will see you in the next lecture.